Alright, G. So we're starting with this chapter. The first thing that we need to understand in this one is to understand the potential divider circuit, right? And then he asks us to understand the potentiometer. Now, first, let's get on with the potentiometers. You have seen this as a common example in daily life with a fan dimmer, the thing that you use to control the speed of the fan, right? So what does it look like from the inside? This is what it looks like from the inside. It has 3 terminals. And the way we use it to create that variable voltage or variable resistance effect is that there are 3 terminals to this. So the current enters from one terminal, and now it has 2 choices. It can either leave by covering this whole path and then entering this strip and then leaving the second terminal. Or if you are using it that way, then the current enters from this path, then completes the whole circuit and then leaves the third terminal. When you use it this way, then of course you're using this resistance of the whole strip. This is the carbon strip that we're talking about. You're using it completely. So you're using it effectively as a fixed resistor. If you want the variable effect, then you need to use this red path in which you can twist this rod and change the position of this wiper. Now, as you change the position of this wiper, the length of path is changing from this point to that point, XYZ, whatever that is, right? And we understand from physics that the resistance of a length of wire or a piece of strip is proportional to the length of path, right? So the more highly resistive path you cover, the higher the resistance of that part is going to be, okay? So similarly, this is what you're using in daily life to control the speed of the fan. Now, we want to understand what are potential divider circuits, okay? So we understand point number 2. We're going to get to that later, that how potential differences are compared and how we can use it for other things in the circuit. But first, let's see what are potential dividers, okay? So potential dividers, first, let's look at the formula for potential divider. Now, the formula goes something like this. Whatever voltage you want to find out of XYZ, whatever resistor that may be, you keep the resistance of that resistor in the numerator, divide this with the total resistance, multiply this with the EMF or the battery or the voltage that you want to share. That will give you the voltage or potential difference of that respective element. I will show you an example of this as well. So again, keep this formula written down somewhere and we're going to use it. So basically this formula actually stems from O levels, which says that the ratio of resistances in a series circuit is equal to the ratio of their individual voltages, right? So when you rearrange this, keeping in mind that R2 can be replaced as total resistance and V2 can be replaced as EMF, when you take this to the other side, this is what that formula ends up looking like, right? But this formula is very, you can say its utility is very high, because not only it is used to compare the EMF and voltages, it can also be used to compare voltages and resistances of 2 entirely different resistances of a circuit. I will show you this formula, how to use this formula in an example in which this is the format, right? But let's move on towards the potential dividers. Basically, what you are required to understand and link is that the resistance of LDR and the resistance of thermistors are, of course, inversely proportional to their respective properties, but how are they going to respond to a circuit in terms of current and in terms of voltage, okay? Now, when you talk about current and voltage, the very first thought process that you need to start your question with is going to be the change in voltage, because that is the easiest one to identify and easiest one to discuss. Okay, so for example, if we had a circuit like this, we had a fixed resistor and then we had, let's say, an LDR in this, and we understand that the resistance of LDR is going to change based on the light intensity. So there are going to be 2 circuits, there are going to be 2 resistances. Probably in daylight that is 50 ohms, and at night time it's possible that it is 1000 ohms, right? And the fixed resistor is there to control any short circuits or any high values of current when the resistance of the LDR falls too low. Probably this is, let's say, 500 ohms, right? And this is probably, let's say, 12 volts of supply. Now, if you're dealing with daytime, when the resistance is 50 ohms, then you can see by the potential divider formula that this is going to come out something like this. So 50 divided by 50 plus 500 is going to be 550 multiplied by the battery voltage which you're sharing is going to give you a certain answer. At night time, the picture is a bit different. Although the voltage divider rule says that now I should use 1000 because the resistance has increased, divided by 1000 plus 1500, the total resistance, which is 1500 multiplied by 12. You will notice that this answer will be larger and this answer will be smaller. Although we've compared the voltages, but what happens to the value of current? Of course, when you increase the resistance from 50 to 1000, the total resistance of the circuit previously was 550 ohms. Now it is 1500 ohms. The current will decrease because we are using V equals to IR, right? And the voltage is still the same. It is 12 divided by R equals to current. If you increase the resistance from 550 to 1500, the current will drop. But the voltage is increasing because of simply the idea of voltage divider or potential divider circuit, right? Let me show you an example in a live simulation, right? So we have something like this over here. Right now, let's open the switch. The switch is open. There is no current in the circuit, as you can see over here. There is 0 amperes of current, and I'm not connecting the voltmeter somewhere, right? So let me write down the formula on the screen. Right now, we can see that they are equally divided. They have equal resistances right now. So this is 10 ohms. This is also 10 ohms, right? And we have approximately 10 voltage or 10 volts of EMF. What happens if I change the resistance? Right now, let's compare the voltages. If I close the switch, there is 0.5 amperes of current, and which is, of course, easily verifiable by V equals to IR. If I compare the voltages like this, you can see that 10 volts is equally divided between 10 ohms over here and 10 ohms over there, right? It's over here for this resistance and for this resistance as well. Now, for example, by a chance, I were to increase the resistance of the resistance where the voltmeter is connected. What is going to happen? Let's disconnect the voltmeter, right? And let's change the resistance of this resistance. Now, notice that if I increase the resistance, the current has also decreased from 0.4 to 0.25 amperes. This is what I was talking about, that when you change the resistance, be that because of LDR, be that because of the thermistor, the current will decrease or increase based on the total resistance of the circuit, but it will still increase the voltage if you are increasing the resistance. Now notice that previously the voltage was equally divided. What's going to happen now? Let's apply the voltage divider rule over here. We have 30 divided by 30 plus 10, which is going to be the total resistance, 30 by 40 multiplied by the EMF, which is 10 volts. If I do this, the voltage will come out as 7.5 volts. Now, this is a calculation. Let's try to verify this, whether I get this answer or not. So let's connect the voltmeter over here and the voltmeter over here. So answer is 7.5. And let's change this value live. If I keep increasing the resistance, you can see that the voltage share increases, although the current in this ammeter is decreasing, right? So, and we can verify this rule as well, that highly resistive circuits or highly resistive resistances are going to consume a larger portion of the total voltage, which was 10, but now it is getting a higher share of 8.18 volts, right? So this is what he wants to test. Can you figure out that the current decreases or increases, provided that the voltage can do the opposite thing, right? Okay. So we understand point number 1 and point number 2 of potential divider and voltmeter. I will also add the link of the video in which I have solved questions regarding this, okay? Let's move on to null method, right? This is the main topic of this video, and I'm going to skip point number 4 because I've covered this in another video, the potential divider circuit using, of course, LDRs and thermistors. I've covered this in another video. I'm going to focus on point number 3 because this question or these type of questions don't really come in the paper, but when they do, they're practically unsolvable. Let's move on to what do we mean by that. So null method, null basically means zero or empty. If you're a computer student, you will understand what null means, but basically over here we're using it as a term of zero. What we are trying to do is, what's the zero we are looking for? So practically voltage may be zero or the current may be zero at that certain point. Okay, now where will we find this? Now primarily, previously, it was known as Wheatstone bridge, okay? For those who might have studied this before, may be familiar with this, but Wheatstone bridge by this name is not in your syllabus anymore, but you will find questions regarding this. I will show you a few examples, okay? What was this circuit used for? You can see over here that primarily the target of this circuit was to find out the unknown resistance. Why do we want to find the unknown resistance if we already know the resistance of this component? For example, we can use voltmeters, we can use ammeter to find out the resistance of this component. And what's the need of this circuit to find out the unknown resistance? Basically, all your instruments in, you can say, in physics, in engineering, and in sciences, all instruments that measure temperature, that measure, let's say, pressure, that measure, let's say, flow rate, that measure, let's say, the amount of chemical that is being added into something while making a fertilizer, or let's say making a lead acid battery, all those instruments are basically resistive in nature. So what we do is connect an instrument between these two terminals, which is placed very far away from the control room. So when the resistance of that component changes, the values of the whole circuit change. When the circuit's value, voltages, and the potential differences change, they are calibrated to represent what this instrument is measuring, right? So basically this circuit is used for instrumentation and detection, but that's beyond the scope of the syllabus. So I'm just going to stick to how to solve the circuit, what the circuit is trying to achieve. So the target is to find out this unknown resistance, and by of course, by derivations and formulas, it comes down to this basic idea, or you can say this basic tool is that the product of opposite branches will be equal. It will be equal if the voltage between these 2 points is 0. So if the voltage between this point and the voltage between this point, if the voltage is 0, or if you had connected an ammeter, the current is 0. So 0 volt or 0 ampere, whatever comes first, whatever comes in the question, that is going to be, then in that situation, the product of opposite branches will be equal. So for example, R3 multiplied by R2. So R3 multiplied by R2 will be equal to R1 multiplied by Rx. Now, since Rx is the unknown, this is what you're trying to find out. So we make this the subject of the formula and we get to this equation, that R3 multiplied by R2 divided by R1. Okay. But please be advised, this can only be used when he mentions that the ammeter or the voltmeter are in a null condition, that they are showing a 0 value, which means that the voltage of the electron reaching at this point and the voltage of electron reaching at this point is practically equal. What does that mean, by the way? If you had seen my previous videos explaining what is potential difference, you will realize what I'm trying to say here. So let's say if this voltage was 10 volts, the electron reaching at this point has 10 volts, and the electron exiting from this point has 0 volts because it has to go back to the battery to get recharged. Anyways, when it comes to this point, of course, it is passing through this resistor. It has to lose some energy. Let's say that this voltage becomes 8 volts. So this resistor is using 4 volts. 2 volts. What if the electron reaching at this point also ends up having 8 volts, although these resistances are not supposed to be equal, or you can say they can have different values. They are not supposed to be exactly same, although their ratios will determine what voltages are going to come back. But anyways, if this is 8 volts as well, what will happen now? So the electron coming at this point and at this point has equal voltage. If you were to connect a resistor at the center, or if you were to connect a voltmeter at the center, it will notice that both branches or both terminals have same voltage. If the voltage is same, then the potential difference, which is 8 minus 8, is going to come out as 0. This is what we're talking about. Null voltage, null current, no current, which means that the voltage points, the nodes at these two extremes, have the exact same voltage, which gets me back to this equation. This is what we get, you can say, as a result of this null condition. And if I know this null condition, then R1 is known, R2 is known, R3 is known, because I put them there. Rx is unknown. This is what we don't know, because remember, it is connected in the field and it is trying to measure a temperature, pressure, or something. Okay. All right. This is an example taken from the internet. You can try to solve this. If it was a null condition, then of course, one of the resistors would be missing. And if it was a null condition system, then what would have happened? These opposite branches product would be equal. So you could simply would have done 4 multiplied by 5 would have been equal to 7 multiplied by some, let's say, Rx, if this was not given. Then you could have found Rx, right? Now let's try to solve a question regarding this. Now notice what is mentioned. The ammeter is 0, which means this is a question of null method. There is no current in the branch, which means that the voltage at this point and the voltage at this point are exactly same, setting up no potential difference or 0 potential difference, since there is no current. Anyways, what does that mean? It means that the product of opposite branches will be equal. So I can very well say that R1 multiplied by R4 will be equal to R2 multiplied by R3. Please notice that the variables may be different. He can use A, B, C, and D. Okay, so if I choose an equation from this, I will get to the most familiar one, which is R1, R4, R2, R3, which is option D. So this question is based on, primarily you can say based on memory, nothing to think about here, but we understand the logic as I've explained it over here as well. Let's look at another question, very recent, of course, from October, November 2022, right, from paper 1-1. But anyways, let's look at the question. He says that the voltmeter reads 0. You see, as I explained earlier, he can mention whether the current is 0 or whether the voltage is 0. Both will be considered in the exactly same category. Okay, so voltage is 0. That means that the product of the opposite branches should be equal. Let me color code the example. So he wants you to find the value of R. We'll get to that later. But first we need to establish that the product of 10 multiplied by 2, which is going to be 10 multiplied by 2, is going to be equal to whatever this product is going to become. Now we notice that R is in parallel to 8 ohms. And for that, I should calculate this 1 over 8 plus 1 over R equals to 1 over X. I don't know the total resistance. So I'm going to keep X. I'm going to assume that instead of these two, there is only one resistor over here. And I'm going to name it X. So X multiplied by 5 should be my next position. Now when I find X, I can very well see that this is going to become 4, right? This means that 1 over 8 plus 1 over R is equal to 1 over 4. This is going to come out as 4 ohms. Now I can simply use LCM, algebra, and other mathematical techniques to find out that R is going to be equal to 8 ohms. Now let me share another trick with you. I can understand that whatever happens, the combined resistance of whatever that is, I don't know. The combined resistance is actually going to be 4. It's going to be 4. Now this is a trick for parallel resistors, that if there are two resistors connected in parallel to each other, and if they have the exactly same resistance, for example, if this is 10 ohms and this is 10 ohms, I don't need to apply 1 over 10 plus 1 over 10. I can simply use a shortcut that if they're exactly the same, then instead of these two, if I had to replace one resistor, this would be 5 ohms, half of one resistor. And we can replicate this technique with many resistors. For example, if there were 3 identical resistors in parallel to each other like this, let's say there are 10 ohms, 10 ohms, and 10 ohms. What would be the equivalent resistance now? It will be 10 divided by 3. So if you keep on increasing the number of resistances, provided that they are equal, then you can use this trick. So if the answer is 4, that means 8 is actually double of 4, right? Which means that this should also have been 8 ohms. Only then 1 could be halved to make 4, which means that this answer is going to be option D. This is the logical way. This is the mathematical way. Whatever suits you, you can use it. Okay, you can bring this over here and take this over there and then try to solve it mathematically. It's up to you. I have no control over this. So these are the questions that you're going to find based on the null method. Now, there is another situation, there is another topic that generally is not mentioned in the syllabus, but it's going to be part of the syllabus. That is unknown cells EMF. How to find out the EMF of the unknown cell. For example, which is the unknown cell in this situation? You see, before you move on with this topic, please go back and check out the video of resistance equals to rho L over A. This is very important to understand this, because what we're going to use from this equation is rho R proportional to length. This is what the result we are going to use in this part of the video. So unknown cell is this one. Let's call this EX. And this is the driving cell. This is the known cell. We know about this. We know the voltage of this cell. And please be advised that how they're connected. This is positive, this is negative, and this cell is also positive, this is also negative. So both cells are trying to inject current into the circuit like this. Now, what is the formula? What's the theory? What's the full understanding of this? Okay, so what they're trying to do is that the electron is also trying to come from this branch, and the electron is also trying to come from this branch. This section A to B and C, what is this? This is actually a piece of wire. This is actually a piece of wire like this. It's bare wire which can be used to make contact with this galvanometer or ammeter at any point, right? Now, we basically find a balance point, or you can say a null point, exactly the same letter over here. So balance point means that the galvanometer now reads 0 ampere, or could be a voltmeter, reads 0 voltage at this point, which means that the section of wire between A and C has the same voltage as the voltage of the cell. because this resistance piece of wire is in parallel to this cell, and if both are providing the same voltage, that means that the current in this circuit will become zero because there is no potential difference. What does it look like? I'm just elevating the level of this topic, but don't need to worry. So from point A, this is what it looks like, to point C. And this is your unknown cell that you've connected with the galvanometer to point C. If this is, let's say, 10 volts, and if this is, let's say, 10 volts, will there be any current in the circuit? No, because both are trying to connect. Both are trying to conduct electricity in the circuit. Now, please notice that I've just replicated this part of the length of the length up to this point. The rest of course, the wire is still available up to point B. You see, as you move along the length of the wire, the resistance increases, and we know that voltage is proportional to resistance in a series circuit. If you use a high length of wire, which is proportional to resistance, the resistance is higher and the voltage is going to be greater. So the voltage of this cell is known because that voltage is being spread out through this whole length of wire. And that is what we use to our advantage to find out the voltage of the unknown cell. That wherever this galvanometer reading is going to become zero, this is going to be 100% the situation that whatever voltage this wire is consuming, the voltage of this cell is also exactly the same. Now, this is the, of course, complicated theory. How to simplify this, how to use, or how to just use it for solving questions, what to think about, how to look at the questions. I'm going to solve a few questions with that as well. And hopefully that's going to make things easy for you. So let's consider this length of wire. Let's label this as LAC. And let's label this from this point to this point as LAB. And as I mentioned earlier, we're using this relationship. So the length of wire AC is actually representative of resistance of AC. Length of AB is representative of length of the resistance of the section of wire AB, right? Now, what do we see? What are we trying to solve? We're trying to find out the unknown voltage EX. But we're trying to compare the resistances. But do we have resistances with the voltmeter ammeter calculated? No. We have the lengths measured with the meter rule. Physically, this is what we have. This is what we do, right? So we have the data of length, but we're going to replace them, keeping in mind that we're trying to calculate this for resistances. So what does the formula come down to? The formula looks like this. LAC, length AC, which is, of course, we're dealing with resistance, but we can't do that because we can't measure it right now. Divided by the length of the whole section, which is LAB, the whole section, multiplied by the EMF of the known cell, which is the driving cell. Let's call this E0, equals to, is going to give me the voltage of the unknown cell, which is EX, right? And if you notice, this actually comes down or comes from the same idea that the ratio of resistances is actually equal to the ratio of voltages in a series circuit, whatever that may be. This is V1, let's say this is V2, this is V1, this is R1, this is R2, right? This is where the formula potential divider actually comes from. So primarily, this is what they're trying to do. If you take this over there, you will get the formula to look like this. Okay. Anyways, everything is connected. That's why I'm just developing relationships over here. Anyways, you can use this formula to calculate the problems of this question. Let's move on to the solving. Let's move on to the questions. So first, starting with a simpler example so that we understand how to use this. Okay. Now he tells you that this is the driver cell, of course, the voltage of the known cell. He tells you that the voltage of cell X comes out as 1.1. Now this is 1.1 volt. And the galvanometer reads 0 ampere at a length of 0.7. Now, students may get confused that what's the total length of the system. Now, since this is meter rule, this is going to be 1.0 meters, right? Now, he tells you, he asks you, what's the voltage of the second cell, EY, right? Now, first, what we're going to do, we don't know the voltage of the driver cell. If I don't know this voltage, then I can't calculate the value of Y. Although there is a shortcut, but that's for you to figure out. I'm going to solve this with the longer method, which is conceptual and makes this concept easy to understand. So first, using this information, I will calculate the driver cell voltage. So what was the formula? The formula was the length of this section divided by the total length multiplied by the battery is equal to the cell voltage. So 0.70 divided by 1.0 multiplied by the driver cell voltage, which is E0, equals to 1.1. Okay. Now, if I make E0 the subject of the formula, or you can just calculate E0. So E0 comes out as, you can do this with a calculator, 1.1 divided by 0.7. This comes out as 1.57. So this is 1.57 volts. The driver cell is 1.57 volts. Now let's move on to the second step. The second step says, what's the voltage of EY? It is balancing at 0.9. So the balancing length, which is 0.9, divided by the total length, which is 1.0, multiplied by the driver cell, which is 1.57. So this is 1.57. Let's find out this voltage. Multiplied by 0.9 divided by 1 comes out as 1.414. So this is 1.414 volts. Now, this is going to be an answer, right? There is a very large gap between C and D, so no need to get confused. Our final answer is option D. Okay, let's move on to the next question. This will take a bit of your time because it is conceptual. You can see this question is from 2014, paper 1-2. You can open this question up, pause the video and try to solve this on your own based on what I've taught you, or you can just follow the video what I'm trying to teach you over here. Okay. He tells you that there is a potentiometer. Okay, fine. We understand this is galvanometer and there is a balance point reached. He says that the wire PQ is 100 centimeters long and the resistance is 5 ohms. So the whole wire has a resistance of 5 ohms. First, we need to find out the resistance of this section of wire. How can we do that? You see, 100 centimeters, right? So we have 5 ohms of resistance spread over 100 centimeters. So multiply this with 40 centimeters. To find out the resistance of this section. This comes out as 2 ohms, right? Which means that this section of the wire has a resistance of 2 ohms. And of course, if the total is 5 ohms, then the rest of this will be 3 ohms. Okay, fine. Good enough. Okay, let's move on. So the power supply has an EMF of 2 volts. So this is 2 volts. The solar cell has an EMF of 5 millivolts. So this is producing 5 millivolts. Be advised, this is milli and there is no milli over here. Now, when I find milli over here, I can deal it with two ways. I can either divide this with 1000 and write the actual value, or I can just simply write down 5 into 10 raised to the power minus 3 wherever I put this value. Let's move on to the next question. He says that what is the resistance of R so that the galvanometer reads 0? Now, what he's trying to tell you, he's trying to find out the value of R. And of course, this, and these 3 resistors are connected in series to each other. And if there is a balanced point, then most definitely the resistance or the voltage of this section is also going to be 5 millivolts. What is the voltage of this section? I don't know, right? But what we can do over here is just apply a simple formula over here. Okay, how can we do this? We have 2 choices. I can opt for this idea that this 2 volt is actually spreading out throughout the whole circuit. Out of this 2 volt, 5 millivolt are going to be used by this one. Some millivolt will be used by this section, and the rest of the voltage is going to be used by this section, constituting to complete 2 volts. So I'm going to use this formula that the ratio of resistances is equal to ratio of voltages, right? So I understand that the first resistance I have is of 5 ohms, right? I can use 5 ohms, or I can use 2 ohms for 5 millivolts. So I'm using 2 ohms, and in place of this voltage, I'm dealing with this value. So this is 5 millivolts, right? Resistance number 2, I don't know. Let's keep it as unknown. Voltage number 2, let's keep it as 2 volts. Why? Because now I know that this is actually the total resistance. This is 2 ohms plus 3 ohms plus R. But I don't know the value of R, okay? Let's find out the total resistance. Now, when you do this, the total resistance comes out as 800 ohms. This answer will come out as 800 when you finally deal with this. Let me rewrite this equation. This is going to be 2 divided by RT equals to 5 into 10 raised to the power minus 3 divided by 2. When you solve this equation, you're going to get RT equals to 800 ohms. Is this the resistance of this R, or is this the resistance of the whole circuit? This is the resistance of the whole circuit. Why? Because I took 2 volts to represent this resistance, and this 2 volt is being spread out throughout the circuit, right? So 800 ohm is the total resistance, and out of 800, I can see that this wire had a total resistance of 5 ohms. So minus 5 gives me 795 ohms. This resistor must be 795 combined with 5 ohms of this wire. Total resistance 800 ohms. So my answer for this question is B. right? Now, what some of you can do is actually solve this question by unit method. You can find 5 millivolts for this part, then a few voltages for this part, and then ratio method to use this part. You can do that method as well. There is no issue. Okay. All right. Let's move on to this last part. We have diode function. Okay. Now I will add the link of the diode function as well, but to simply put, if you try to conduct, or if you try to provide the current in this direction, the diode will conduct. If you try to set up the battery in such a way that the current is coming from this side, the diode will not conduct. So the direction of arrow of the diode should match. And of course, we're dealing with conventional current, so no need to ask that question again. The diodes have zero resistance when conducting and infinite resistance when not conducting. In which circuit the current is the greatest. So we have to figure out in which the diode are conducting and which situation the diode are not conducting. And of course, the resistance are identical, the batteries are identical, everything is identical. So you can develop a ratio method. First, let's figure out what the polarities of the batteries are. So this is plus minus, so on and so forth. Let's figure out whether the current is going to be allowed to flow. So the current moves through this terminal. Will it be allowed to flow in this branch? Yes. The current direction and the diode direction matches. Similarly, they are connected in parallel. Will this be allowed to pass through? Yes. Let's move on to this one. Current tries to go towards this side. Will this diode allow this? Yes, it will allow this. When the current comes to this side, will it allow this? Yes, it will allow this. So effectively, the circuit looks something like this. A single battery and a resistor, but both are in series. So this will be actually 2R. If I were to simplify this circuit, this actually looks like this. 2 resistors, identical but connected in parallel, right? And if I were to use the formula of 1 over R plus 1 over R to do this, I will realize that this actually comes down to this one resistor that has a value of half the resistance, as I've mentioned in the previous trick. Anyway, so this circuit causes the resistance to be half. This has doubled the resistance. What happens over here? The current will be, of course, it's going to pass through the branch. It is not going to be stopped by anything because there is no diode. But can the current pass through this? No, the current cannot pass through this. The current has this direction. The diode has the opposite direction. It can't do it. So there is only one resistance, R. Okay. What happens over here? Can the current pass through this? Yes. The diode direction, current direction matches. Can the current pass through this? No. The diode direction, the current direction are opposite. So if, effectively speaking, only this current can pass, this current cannot pass. Okay. So effectively speaking, C and D are exactly the same circuits. This is also resistance R. So C and D get eliminated. And we want to find the greatest current. Now, according to V equals to IR, if you want the current to be very high, the resistance has to be very low, right? So I choose option A. This is a technical reason, but the non-technical or the quick method would have been something like this, that the current can go through this branch and it can go through this branch as well. So if the current was I, the current is I, the total current will be 2I from the battery to support this resistor and support this resistor as well, right? So it would have been a quicker, much quicker method than this. So I hope that we understand what we are looking for in the galvanometer's null method. We understand what is potential divider rules. We understand what is Wheatstone bridge, the product opposite product rule. We have solved questions regarding this. Don't forget about this. This is also very important, and this is very important. This is very important question, right? The terminals of the batteries should be exactly the same. This is how he tricked you in May-June 2023 paper. There is a MCQ tricking you into believing that this is the right answer. The question looks like this, but it's actually the opposite answer. Anyways, I hope that you understood what I've taught you. Good luck.